This is the last lesson for Chapter 1, Section 1.6, Independent Random Variables. Recall that for any two events A and B, we say they are independent if and only if the product of the probabilities are same as the probability of their intersection, or the probability of A given B is same as the probability of A, or the probability of B given A is same as probability of B. If at least one condition is satisfied, the other two will be automatically satisfied. The same condition can be used to check the independency of two random variables by replacing event A and event B with random variables x and y. That is, if x and y are independent, the product of the marginal densities will be same as the joint density of x and y for every pair. Here are the definitions. For discrete random variables, if the product of the marginal PMFs, that is Px and Py, are same as the joint PMF of x and y, we can say that x and y are independent. This condition should be satisfied for all pairs of x and y. For the continuous case, if the product of the marginal PDFs, that is fx and fy, is same as the joint PDF fxy, then we say x and y are independent. Let's look at an example. Suppose the joint PDF of x and y is given as follows. Can you show that x and y are independent? Let us first find the marginal PDFs. To find the marginal PDF of x, you have to integrate the joint density over y. The support of y is from 0 to 1. So, we integrate the joint PDF y from 0 to 1. You end up with the answer e to the negative x. Now let's find the marginal density of y. In order to find fy, we integrate the joint density over x. The support of x is greater than 0. That means you have to integrate the function from 0 up to infinity. If you do the integration, you will end up with the answer 2y. Now we can write the two marginal densities as follows. Now let's check the condition. We are going to multiply fx and fy and check whether the answer is same as the given joint PDF. If you multiply fx and fy, you will end up with 2y e to the negative x, which is same as the joint PDF. Therefore, we can say x and y are independent. Here's another example. Look at this joint PDF. In this function, the support of x is from 0 to 1 and support of y is from 0 to 2. Are x and y independent? Again, let's find the marginal PDFs. The marginal PDF of x can be found by integrating the joint PDF over y, that is y from 0 to 2. After you perform the integration, you will end up with 3 over 5 times 2x squared plus 1. If you want, you can leave the answer without simplification. Now let's find fy. Again, we integrate the joint PDF over the support of x, which is from 0 to 1. If you do so, you will get the answer 3 over 5 times 1 over 3 plus y over 2. Now we can write the two functions in the proper way with their support as follows. In order to check whether x and y are independent or not, we have to multiply fx and fy and see whether you can end up with the given joint PDF. Now if you do so, you can clearly see that the product of fx and fy is not as same as the given joint PDF. Therefore, x and y are not independent. Let's check this condition for the discrete case. Recall example 1.1. Here is the joint PMF and the marginal PMFs. We have already calculated the marginal PMFs in section 1.4. Are x and y independent in this situation? For the discrete case, we have to check the condition, that is, the product of the marginal PMFs is same as the joint PMF for all possible pairs of x and y. In this example, there are 4 possible pairs of x and y. They are 1, 1, which is x equals 1 and y equals 1, 1, 2, that is x equals 1 and y equals 2, and so on. The condition, the product of the joint PMFs, that is px times py, should equal to pxy for all possible 4 pairs. Remember that if at least one pair violates the condition, then x and y are not independent. Now let's check all 4 pairs. For the first pair, 1, 1, if you multiply the marginal density of x at 1 and marginal density of y when y is 1, and check the answer with the joint PMF, which is the value you find in the cell 1, 1. Let's go back. So here's the cell for 1, 1. If you multiply the PMF when x is 1 is 8 over 18. When y is 1 is 7 over 18. When you multiply these two, you have to get 3 over 18. But we clearly see that if you multiply px and py, you cannot get pxy. Now let's check the other pairs also. If you check all these 4 pairs, you will see that none of the pairs satisfy the condition and x and y are not independent. Since if at least one pair violates the condition, you can conclude that x and y are not independent. When you find that for the first pair the condition is violated, you can stop checking the other pairs because at least one pair violates the condition. There's no need of checking the rest because x and y are not going to be independent. There is another way to check whether two variables are independent or not by separating the joint densities. Suppose x and y have the joint PDF fxy, which is positive if and only if x has the support from a to b and y has the support from c to d for some constants a, b, c and d. Then we say x and y are independent if and only if you can find two functions, that is gx, which is a function of x alone, and hy, which is a function of y alone, for the given joint PDF, then x and y are independent. Here gh should be a non-negative function of x alone and hy should be a non-negative function of y alone. So, if we can split the JPDF into two functions x alone and y alone, then we can conclude that x and y are independent. Let's try an example. Look at this joint PDF. The support of x is from 0 to 1 over 2. The support of y is from 0 to 1. Are x and y independent? Now what we have to check is whether we can split the function 8x into two functions such that one function contains x only and the other function contains y only. Here is one possibility. If we let gx to be x and hy to be simply 8, if you multiply gx and hy, you end up with 8x. Here, gx contains a function only of x and hy is a function of only y. Here it is a constant, but still you can split it as a function of y. Because you can split the joint PDF into two functions gx and hy, we can conclude that x and y are independent. Are there any other possibilities of splitting this function? Here's another way. We can split the function as gx to be 8x and hy to be simply 1. Still, if you multiply gx and hy, you end up with the given joint PDF, 8x. Therefore, again we can say that x and y are independent. Note that gx and hy may or may not be the marginal densities of x and y. If you want to find the marginal densities, you have to integrate the given JPDF over y and over x separately as we did in section 1.4. After that also, you can show that x and y are independent if the condition is satisfied. Look at this example. Suppose you have the following joint PDF. Be careful that the support of x is from 1 over y to y and the support of y is from 1 to 2. Therefore, the support of x depends on the random variable y. Are x and y independent? Now let's check whether we can split this function into gx and hy. Of course you can do that. Such a way, gx is kx and hy is 1 over y square. But you have to be careful. Although you can split the function, still x depends on 1 over y and y because the support of x is from 1 over y to y. Although you can split the function into gx and hy, because the support of x depends on y, we cannot say x and y are independent. Therefore, if you have to check whether two variables are independent or not, the first thing you have to check is the supports of x and y. If at least one of variables depend on another variable or the other variable, then you can conclude at the very beginning that x and y are not independent, and you can save time on finding the marginal PDFs or splitting the functions into gx and hy. Straight away, by indicating that the support of one variable depends on the other one, you can say x and y are not independent.